Hello, here we are diving into another batch of forces questions. We got the usual skydiver starter again, so we'll make this one pretty quick because this comes up quite a lot, but it's nice to keep going over it to get it cemented in your mind. So he jumps from a stationary hot air balloon several kilometers above the ground. In terms of acceleration and forces, explain the motion of the skydiver immediately after jumping. So acceleration equals g, the free fall due to gravity. Um, so we got that because we want to say acceleration and forces. So we want to say because the drag equals 0 at a time before terminal velocity is reached. So the acceleration is less than g but is greater than 0. We need to have that because the drag is less than the weight, but it's greater than 0, less than the weight of the skydiver. And then at terminal velocity, acceleration equals 0 because drag equals weight. So you've got 2 points you can make on each one. What's going on with the acceleration and how has that come about due to the forces? In the final stage of the fall, the skydiver is falling through the air at constant speed. The skydiver's kinetic energy does not change, even though there's a decrease in the gravitational potential energy. State what happens to this loss of gravitational potential energy. Right, so it's going into heat, sound, all the usual things that we have for losses. So yeah, heat, sound, motion of air that the skydiver is moving through. So all of that is all going into the air in some fashion. Figure 3.1 shows a sketch graph of the velocity, variation of velocity of the skydiver with time. So we've got velocity time graph. Suggest the changes to the graph, if any, for a more massive, so a heavier skydiver of the same shape. Okay, so if we've got that, we're going to have a higher terminal velocity. It will take longer to reach terminal velocity because we have to get the drag up more. It's going to take longer to get to the velocity that we require. Okay, the initial gradient will be the same because we're going to start off with our acceleration being g. So that will start off. So it's going to look something along the lines of it's going to start off much the same, but it's going to take longer to reach a higher terminal velocity if that was your flat bit. So it might take longer, we're at higher, same gradient at the beginning, that sort of thing. Right, so let's push on. Right, now we've got a wooden block motionless on an inclined ramp. The angle between the ramp and the horizontal is theta, which we have in the picture. The weight of the block is already shown, W. Complete the diagram by showing a normal contact force N and the frictional force acting on the block. Right, so we want to try and draw a normal reaction force, which is perpendicular to the ramp. And then the friction is going to oppose the motion, so it will be going up the slope. So that's easy enough to mark on. Remember to put the N and the F on there. Write an equation to show how F is related to W and theta. Okay, so F is, because this is theta coming down here, so F is going to be equal to W sine theta. Easy enough, just resolving parallel to the slope. Right, they seem to have given up on that block now, and we're now looking at a kitchen cupboard, which is resting on a support A. Is there anything in the text that isn't in the question? In the diagram, I mean, total weight of the cupboard and its contents is 200 newtons. They've got that in line of action of the weight is a distance 12 centimeters from A. Yeah, screw securing the cupboard to the wall is 75 centimeters up. Yeah, state the principle of moments. Okay, so I'm not going to write all this out. I'll say it, maybe put a few things down. So for object to be in equilibrium, so that's the first thing. We need to say that we've got some object that's in equilibrium. Then we can say that the clockwise moment about a point You have to have that about a point thing because we need to reference that point later on. Clockwise moments about a point equal the anti-clockwise moments about the same point. So that's why we need that point in there. Otherwise, we can't say that these two things are going to be equal unless we're taking moments about the same point. So you need all of those bits in there. Cool. The cross-sectional area under the head of the screw in contact with the cupboard is 6 times 10 to the minus 5 meters squared. Calculate the pressure on the cupboard under the screw head. So we're going to have to do our moments here. So it's in equilibrium. Again, this is one of these ones where they've given us the perpendicular distances. So remember, with moments, we don't have to take moments along the same line. It's just about the same point. So if we take moments about A, we can say that 200 multiplied by 12 is equal to F multiplied by 75. They're both in centimeters, and these are both of these are perpendicular. We take those distances, these are perpendicular, and that is the thing that matters when you're taking the moment. So that's going to give us the force which is applied here at the screw. So if we divide that by the area, we'll then get the pressure. So yeah, 200 times 12, so the pressure is going to be 200 multiplied by 12 divided by that 75, and then we need to divide by the 6, and let's multiply by 10 to the 5, as in we've already divided by that 10 to the minus 5. So let's make that a 2, so this will become a 400. So we want 400 divided by 75. 5 75s is 375, so that's going to be 5 1/3. So 5.3 times 10 to the 5, because we've been dealing with two significant figures all the way through this. And don't forget your units of putting pascals on. State and explain how your answer to 3 would change, if at all, if the same screw was secured much closer to A. Right, so if it was closer to A, so we need to have moment unchanged. So that's one thing. The moment is unchanged because it's still in equilibrium. So still equilibrium. But we've got D is down, so F is up. So pressure, which is what we're working out in that last part, would also go up because F has gone up. We might as well say as well that A is unchanged, because that's the other thing that comes into the pressure calculation. So we've got that usual chain of things. We're working our way through these formulae that we're using. So the formula for the moment, so the moment's unchanged, is F times D. If D is down, then F is up. And then the formula for pressure, F is up, A is unchanged, so P is up. Just that chain. You can put each one of these on a separate line and you've got a nice logical argument. Yeah, that's a nice beefy question, that one. Well, I was just about to skip on to the next one. I realised I didn't actually work out what F was in part 2. Written out the equation but not done the calculation. So F is going to be 200 divided by 75, which is 2 2/3, multiplied by 12. So 24 plus 8 is 32. So yeah, F is 32 newtons. Sure you can work that out for yourself, but it's nice to be complete. Right, next question. In February 1999, NASA launched its Stardust spacecraft, to collect dust particles from a comet. After a journey of 5 times 10 to the 12 meters that took 6.9 years, it came back with a whole load of dust particles. All right, so they've got some kind of gel. You stick the gel out and then the dust buries itself into the gel. Yeah, clever. Length of the track is typically 200 times the diameter of the dust particle. Right. Calculate the average speed of Stardust during its voyage. So it's gone 5 times 10 to the 12 meters in 6.9 years. So 6.9 multiplied by, well, seconds in a year, 3.365.25, just to add in that quarter day. So that's the number of days we've got, multiplied by 24 hours, multiplied by 60 minutes, multiplied by 60 seconds. So yeah, a lot of annoying numbers. So they might actually give you that number of seconds in a year in the formula booklet. I can't remember nowadays. So 6.9 times 365.25 times 24 times 3600 is that. And then we have to, what was it, 5 divided by that is something small. So we've got 2.296 times 10 to the 4. So what's our accuracy here? Again, two significant figures. So 2.3 times 10 to the 4 meters per second. Yeah, I don't usually, you might notice there when I'm reading it out, I don't tend to put all of the 10 to the power whatevers into the calculations. So I just did 5 divided by the denominator. It left me with a 10 to the minus 8, and it's just easier to not bother typing it in and then deal with all the 10s at the end. But, you know, each to their own on that. But I see a lot of people make a lot of calculator mistakes where they're trying to put too much into the calculator at once, and then they can't see that they've got it wrong, or, you know, unpick it. So the more chunks you can break it up into and leave bits out is often for the best. Calculate the average stopping force produced by the gel for a dust particle of diameter 0.7 millimeters, mass of that, traveling at a velocity of that, relative to stardust. Okay, so that's telling us the stopping distance on all of this, isn't it? So we want the average stopping force. So we've got a mass. I think they told us, here we go. So it's 200 times is the diameter. So we can do 200 times this. So yeah, we've got we want to get it all into meters per second. So that is so if it's 0.7, then we've got that in meters. We need to multiply that by 20. So we can get rid of that and then double this. So we've got 0.14 meters. That's how far the particle has gone into the gel. We've got the mass, and yeah, we've got this velocity here. There's a number of different ways you could do this, but they more or less come out as being the same thing. It's variations on the v squared equals u squared plus 2as is what we're getting on this in order to work out the acceleration, because remember, this is our conservation of energy SUVAT equation. So we've got a 0 here, so we're going to get a magnitude of the acceleration by saying that 6.1 squared times 10 to the 6 is divided by 2 times that. So let's just make that a 0.28. That is going to be our acceleration. And if we divide then the acceleration by, multiply the acceleration by the mass, then we're going to get the force. So that's A. So the force is going to be that times 4 times 10 to the minus 6. So the 10 to the 6's are going to disappear. So we're going to have 4 times 6.1 squared divided by 0.28. That's our final thing on this. 4 times 6.1 squared is that, divided by 0.28 is 530 newtons, well, 531.6, so 530 newtons to two significant figures. So yeah, whether you've decided, sometimes people are thinking, oh, should I approach this as SUVAT, or should I approach this as conservation of energy, where they're actually the same thing, as we've seen time and time again with all of this. Right, last one up for this video, and this looks a little bit different. We've got several forces acting on an object that's free to move. So we've got this square which has got 4 forces pulling it in different directions. Using simple calculations, deduce whether the object will move into region 1, 2, 3 or 4. Oh, it's obviously going to move into 3, so we need to say why. So we can say, well, horizontally, it will move to the left because 8 is greater than 7, and vertically it will move down because 12 is greater than 10. So we're just resolving horizontally and vertically. And then we can say, well, therefore, it's going to move down and left, which is towards 3. State the principle of moments. We've already done that in this video. So quickly, again, the sort of things you need. We need to measure that is for equilibrium. We need anti-clockwise moments about a point. So we have to mention that is equal to the clockwise moments about the same point. So they're the key things that you have to get in, but we've already done that earlier on. So let's push on to what looks like it's going to be moments to wrap up. We've got this suitcase. They've given us a lot of information already on the picture. Is there anything not included? Right, so the 50's there, the 46 is there, the 32 is there, so we're looking good already. By taking moments about P, calculate the mass of the suitcase. Right, so they've given us perpendicular distances on both of these things, so we don't have to do any resolving or anything like that. We're going to have that 50 multiplied by 46 is equal to well, mg, because we're going to want to get to m rather than just putting the weight in, times 14. So m is going to be equal to 50 times 46 divided by 14g. The fact we got a g there, there's not really much point in doing any kind of simplification before sticking it in the calculator. So we've got that divided by 9.81 gives us 16.746. So we'll say, yeah, well, 16.7 kilograms, and I'll say 17 kilograms to two significant figures because they haven't really given us anything more than that in the question. So yeah, nice quick one to finish on.